Okay, we have one more speaker, and I don't know if you've been noticing, but our last speaker, Lauren Griffith, has been sitting here running the slideshows all day. So I think we owe her congratulations for that. Lauren is I can read that. Lauren is a graduate student at the University of South Florida in the School of Geosciences, and has been a research assistant at our lab, Everglades Wetland Research Park, since 2015. She got her master's on me and liked it so much she stayed in the same chair and now pursuing a PhD at the University of South Florida. Her work is in, her PhD work at least is dual. She's working in the freshwater wetland that she will be describing here, but she also wanted to do something a little more marine. So she's also doing carbon work in mangrove swamps, both in South Florida and in Puerto Rico. So she's got a full plate of work to do for her dissertation. So Lauren, the floor is yours. And she has to change even the slides here. Is the clicker up there? Oh, you got it, okay.
All right, so I am Lauren Griffiths. So I am going to be talking about a wetland in Florida, looking at the nutrient retention of a created wetland that's designed for stormwater treatment in Naples. So we've heard a lot today, especially this morning, about nutrient pollution, specifically looking at nitrogen and phosphorus and how that causes eutrophication problems around the world. And what we're looking at, especially in Florida, we get a couple of different issues because all of our water starts out in the freshwater systems, where we get a lot of problems like this blue-green algae that comes out of Lake Okeechobee and then hits the coastal waters and causes red tide in the coastal waters because of those high nutrient values. And so in Naples specifically, there was a problem with high nutrient stormwater runoff, and Naples stormwater had about 1 to 2 milligrams of nitrogen per liter and 0.1 to 0.35 milligrams of phosphorus per liter. All of this water was running into the Gordon River out into Naples Bay and the Gulf of Mexico, which is where you get, in these bays, you get the eutrophication, the blue-green algae, and then out here in the Gulf of Mexico, it turns into red tide. So just to give you a little bit of a comparison, the Gordon River watershed, which is where my research is based out of, has about 17.6 square kilometers of water that is then going into this wetland that I'm going to be looking at, compared to the Maumee River watershed, which is, what's that, 100 times that size. But the phosphorus loading per square kilometer per year is higher in the Gordon River, which is all urban stormwater runoff. So this is all the fertilizer that people are putting on their yards and putting on their golf courses, is causing higher weight per area of nutrient pollution. So we've heard about wetlands being used for pollution treatment. A lot of research has gone into domestic wastewater treatment, so tertiary treatment of domestic wastewater. And then we've heard a lot about agricultural runoff and how wetlands can be used for that purpose as well. Not very much research has gone into how stormwater runoff can go through wetlands and be treated. So that's kind of what I'm focused on here. And we're going to keep these numbers in mind. Creative wetlands, as a global average, can retain about 40% of nitrogen and phosphorus. So we're going to keep that in mind when we're looking at Freedom Park and how it is successful. So the objectives of this study are to examine how effective these created wetlands are in protecting the downstream ecosystems. So you've got these urban stormwater runoff, all of the drains that would normally bypass these wetlands that were created would end up here in, this is Naples Bay, which is covered with tidal creeks and mangrove systems. And then we've got the Gulf of Mexico just on the other side. And so specifically, I'm looking at how nitrogen and phosphorus concentration patterns change through the wetlands and where specifically they're being removed and retained and what those processes are. Looking at how efficient the nutrient removal is based on different flow conditions, seasonality, also vegetation conditions. And I'll look a little bit at temporal and water quality patterns, especially during hurricanes and big storm events in South Florida, which is a big problem when it comes to an artificially created system that can only pump so much water into it at one time. And then also the relative role of different processes in the nutrient retention of the system as a whole. So this is Freedom Park. It's located down here in Naples, Southwest Florida. And this is that watershed that I was talking about before. All the water in this area gets pumped through this little tiny wetland down here. All of Freedom Park is about 20 hectares, so about 50 acres, but that includes a lot of paths and parkways, as well as this restored hardwood hammock on this side. In terms of actual wetlands, that's just this side here of created wetlands. It's about 4.5 hectares. So that accounts for this stormwater pond. The water gets pumped in from this little tiny spot. If you see it at the top, my hand isn't stable enough to even point to it. That is the stormwater inflow. So all of the water from Naples comes in there, gets pumped into this pond, and then goes based on gravity through these 3 wetlands here, before going and diffusely entering the hardwood hammock, going out the Gordon River on this side into Naples Bay and then the Gulf of Mexico. So when Freedom Park was originally created, it was owned by Collier County, the piece of land was. They wanted to reduce nutrient loads to Naples Bay and the Gulf of Mexico. So they came up with these 4 preliminary goals for the park as a whole. And one of the problems that we're going to see is how having 4 goals that kind of contradict each other at times causes issues, because there are times where having a water quality goal where you want 80% reduction of phosphorus isn't going to be possible when you also want 75% yearly inundation in a place where the soil is basically sand. And so when there's no water during the dry season, you're not getting 75% of a yearly inundation. And then also this recreational and aesthetic goal, where basically we want it to look pretty and have pretty plants, but that doesn't necessarily match up with some of the other goals. So we did about a 2.5-year study of nutrient sampling, where at different points through the pond and the wetland, and then finally out in the river, we took about 12 samples every 2 weeks for 2.5 years. And we got some pretty interesting numbers. So this is just looking at a 2-year snapshot of that. And this is for total phosphorus. You can see for a majority of the time, our inflow concentrations in blue are higher than our outflow concentrations. The one exception would be right here in 2017, when we had no rain for about 6 months, and then all of a sudden in about a 24-hour time frame, if we put the hydrology of the wetlands on top of this, the amount of water in the wetlands as a whole went up about 5 feet. So because of that, just the sheer volume of water entering the system, resuspending a lot of the phosphorus that was being stored there, we got really high outflow concentrations. But once the system kind of came back to normal, we came back to some sort of equilibrium where inflow concentrations are higher than outflow. And so that's what you see here in terms of average total phosphorus concentration, where the pond is the beginning of the wetland system and wetland 3 is at the outflow. On average, you've got lower concentrations at the outflow than the inflow. But what's interesting is that this actually happens, a majority of the phosphorus retention is happening in wetland 3. The first 3 wetlands, what we think is happening is that this system has been going for about 10 years now, and they are just starting to become saturated with phosphorus, the soils are. And so instead of retaining that phosphorus, they have nothing else to do with it, and it's starting to become a source of phosphorus via resedimentation. And so wetland 3 here is doing a majority of the work for the system, and you're gonna kind of see that with the vegetation as well. That's where a lot of the woody vegetation is starting to flourish. You got a lot of phosphorus, and so they're doing the job there at that final section of the wetland. But still overall, on an annual average, we get about a 55% reduction of total phosphorus, which is well above that 40% annual average. So as a whole, despite it starting to kind of decrease retention at the beginning, the wetlands seem to be doing a good job at retaining nutrients 10 years after construction. In terms of nitrogen, we see something very similar. Inflow concentrations are higher than outflow concentrations until we get a big rain event kicking off our rainy season. Nitrogen in general is a little more tricky just because of how these wetlands are pumped. So there is a lot of fluctuation between aerobic and anaerobic periods of time. So that's where we get some of these values crossing over between inflow and outflow. But still, as a whole, over these 2 years, we're seeing inflow concentrations significantly higher than outflow concentrations. And most of this reduction seems to be in organic nitrogen versus nitrates and nitrates. And again, these first couple of wetlands and the first pond aren't retaining as much nitrogen as we would like. They're actually becoming a source. As a whole, we're getting 26% reduction of nitrogen, which is better than nothing, but we need to be focusing more on those nitrate and nitrite levels and figuring out why we aren't seeing the reduction in those that we would like to. So seasonally, there's some differences. Both phosphorus and nitrogen removal were greater during the wet season than during the dry season, but it's for different opposite reasons, I guess. Phosphorus is up here on the top. If we're looking at phosphorus inflow versus outflow during the wet season, the inflow concentrations are greater in both the wet and the dry season compared to the outflow. But the outflow is the same, whether it's the wet season or the dry season. So what this indicates is that more pollution could be treated, more water could be pumped through this system, because it doesn't matter what those concentrations are coming in, the outflow concentrations are very similar coming out. In terms of nitrogen, you see the opposite. Inflow concentrations are the same, whether it's the wet season or the dry season. But in the wet season, when more water is being pumped through the system, you're getting lower overall concentrations. So for nitrogen removal efficiency, that hydraulic loading rate and the amount and velocity of water going through the system is really important for nitrogen retention. So really quickly, I'm going to go through some of the ways that nitrogen is being retained. This is kind of where my research has been focusing in the last few years, but I'm just going to give you some of the preliminary information and not go through it too much. So this is the overall nitrogen budget in terms of what's coming into the system and coming out of the system based on that 2 years of nitrogen data that we got. And we found about 4 grams of phosphorus per square meter per year being retained in the system, and about 11.5 grams of nitrogen each year. And I'm focusing on these different mechanisms of nitrogen retention and phosphorus retention as how they could be stored in the system. So for the nitrogen budget, still trying to work that out. We think there's a really big atmospheric input, especially during the rainy season, in Naples, there's a lot of cars that drive on 75, and that could be a major source of nitrogen going up into the atmosphere and coming down in rain. Because what we're seeing is that sedimentation accounts for twice as much of what we think is being retained in the system. So there's obviously an additional source. We just don't know where from yet. Phosphorus, we have a little bit better of an idea. Algae is taking up about 40% of the phosphorus, whereas the remaining 60% is going on below the ground in sedimentation and vegetative uptake. So some of the issues that we were looking at researching in Freedom Park include their problem of exotic vegetation invasion, which for them, anything exotic is a plant that was not planted when they created the wetlands. So it's not actually exotic vegetation, it's more unwanted vegetation. And this includes things like willows, because they grow too tall and so they aren't pretty to look at. So they want to remove all of the willows because it blocks the views of people walking on boardwalks. And then this is what we were looking at just now, those nutrient removal efficiency trends and some of the hydrologic influences on vegetation. But specifically looking at this exotic vegetation issue, it's kind of hard to see, but down along the bottom, we've got different species of vegetation that is out at Freedom Park. And then we have phosphorus concentrations. In terms of plants that they consider exotic, that they want removed, about 4 of the top 5 plants that are retaining phosphorus are the plants that they want out of the system. Similarly, if we're looking at here, it's the weight of phosphorus being stored in the vegetation at a snapshot in time. You're getting 3 of the top 4 species that they want removed. So in this case, you have a direct issue between their unwanted vegetation and nutrient removal. And so there kind of has to be a choice that's made of what is the most important. Something else that's really cool that we were able to do is out at Freedom Park in 2016, we put some of these auto samplers at the inflow and the outflow, and they collected samples every 6 hours for 6 days. Almost exactly a year later, Hurricane Irma came through. So we ran out there a few days before the storm hit. We strapped these down with bungee cords and chains and duct tape, hoping that they weren't going to get blown away. And somehow, this is the only sample that we got for the entire year where we did not lose a single sample. So we actually have some really cool data to look at because of the hurricane. And so it's hard to see, but this red point right here is Freedom Park. And this is the eye of Hurricane Irma coming over us. So that happened on September 10th, 2017. So we have some cool data from that. And we're able to compare an average to slightly above average storm event to a hurricane. So here on the top, we have 2016, which is a normal rain event in Florida. We got about 4.5 centimeters of rain in about 3 hours. So every afternoon, this is what you expect, is a couple inches of rain hitting, and it'll quickly go away. The next day, next afternoon, it'll rain again for a few hours. So this is what we expect for an average rainy season. Compared to Hurricane Irma, where we got 26.5 centimeters of rain over 36 hours, most of that happening in this 2 to 3 hour time frame right before the eye of the storm hit. And so this will kind of show us how these created wetlands are going to be able to hold water and what that capacity is for them to retain nutrients in these really high flow conditions, especially 10 years after they're created and they're already kind of losing their efficiency at removing nutrients. So what happens when we add a whole lot of water to that? So in an average year, we get a peak of inflow concentration of phosphorus. In this case, we're looking at this big rain event. About 12 hours later, the inflow concentrations of phosphorus peak. It just takes that amount of time for the rain that hits any given point in Naples to travel down the storm drains into Freedom Park and get pumped into the system. And then about 18 hours later, that same peak is what you're catching at the outflow. But what you see here in a normal rain event is the inflow concentrations are always higher than the outflow concentrations. And really, you only get this one peak, maybe 6 hours later. You have another peak of outflow concentration, but phosphorus concentration levels remain low for the rest of the time. It kind of reaches back to an equilibrium really quickly. Here during a hurricane or during a really large storm event, you get this peak in the inflow, but because you're getting so much rain on the system and so much runoff from the surrounding areas, you don't get that very distinct peak in the outflow. It's a lot more of a slow increase of phosphorus over time, and you don't get that return to equilibrium that you got in a normal storm event. Phosphorus elevations at the outflow remained high for the remainder of the 5 days that we were collecting samples. Also for nitrogen, like I said before, for just the 2 years of nitrogen data we were looking at, nitrogen's a little more hit or miss based on what kind of microbial activity is going on there at that time. But for an average storm event, you see something very similar where you get a peak of inflow nitrogen concentration about 12 hours after the storm. And then again, a peak of outflow concentration 12 to 16 hours later. But the nitrogen concentration remains low. It never really increases. It never really goes above the inflow concentrations, with this minor exception, which I would have loved to see what continued to happen after that, but we'll never know. For the hurricane, you see something completely different. You've got inflow concentrations which quickly decrease, probably because of the sheer volume of water that's coming in. You're just getting it all diluted, all of the nitrogen diluted. But the outflow concentrations remain above the inflow concentrations for almost the remainder of the time that we're sampling. So nitrogen was a huge export in this system. Phosphorus, in terms of mass, there was also an export of phosphorus, not anywhere near the volumes that we saw here in nitrogen, which is the major concern with red tide, is these big exports of nitrogen. So overall, what we're looking at Freedom Park is that nitrogen retention is efficient there. It's losing a bit of efficiency, but not nearly what we're seeing in terms of phosphorus efficiency. Nitrogen retention is dominated by sedimentation. So in order for these systems to be more efficient in nitrogen removal, we need to focus on microbial activity and vegetative uptake. For phosphorus retention, it's losing its effectiveness. It's actually starting to become a source of phosphorus. And so this would be interesting because we're at about the 10-year time mark. So if we're looking at something like wetliculture, this would be past that point where you would be flipping those, and they wouldn't be a source for the water necessarily. It would be a source for the agriculture to be taking up the nutrients. And most of the phosphorus retention is being dominated by algal uptake. So in order to increase the efficiency of this phosphorus removal, we really need to focus on sedimentation and decreasing the resuspension that we're seeing out there. This system could be treating more stormwater or stormwater that has higher concentrations of nutrients in it. But this is only really during normal wet season conditions. During really big storm events, there's already an issue with there being too much water that just gets flown through the system too quickly that it can't actually treat it. If there was a way to retain that water in the system, or if there were additional wetlands for that size of a watershed, we would see different results. So ultimately, retention is the most important. We should be focusing on nutrient retention, not necessarily pumping as much water as we possibly can through the system. The wetlands are designed to treat normal stormwater conditions, like I said, but they should be designed with a better understanding of these extreme storm events, especially in times like today where we're seeing more extreme storm events with more intensity, and we aren't really creating wetlands with that design and that purpose in mind. And the priorities really need to be implicitly stated prior to creating the wetlands in order for them to be managed for those goals. So again, here I'm talking about those exotic vegetation species and whether or not we want a wetland to be pretty and be able to walk your dogs in it, or if we want it to be used for water quality and nutrient retention purposes. And in order for real changes for nutrient issues to occur, we need big landscape scale alterations in order to retain the nutrients on the landscape instead of putting them into our waterways. So that'll be it.